Assume that the algorithms considered here sorts the input sequence in ascending order. If the input is already in ascending order, which of the following are true? 1. Quicksort runs in theta n square time. 2. Bubblesort runs in theta n square time. 3. Mergesort runs in theta n time. 4. Insertion sort runs in theta n time. And 4 options are given. We need to find out which of these statements are true. So this is a question regarding sorting algorithms. So we will go through these statements one by one. If you take a look at statement 4, it says that insertion sort runs in theta n time. Now that is true. The best case running time of insertion sort is theta n when the array is already in sorted order. Why that happens is, what we do in insertion sort is for I equal to 1 to n, for each element a of I, we will assume that the array to the left side of a of I is already sorted, and we will try to place a of I in some position in the left side array to the left side of a of I, such that it will be in the sorted position. Now if the array is already in a sorted order, we don't need to make any changes for each element a of I that we are choosing. So we will only do one sweep of the entire array, and we won't be making any changes in that sweep. So it runs in theta n time. So saying that insertion sort runs in theta n time is true. Yes, that is the best case of insertion sort. Then that happens when the array is sorted. 2. Mergesort runs in theta n time. Now that is false. Even the best case of Mergesort algorithm is theta of n log n. Now saying that Mergesort runs in theta n times is false, because whatever options, even if the array is sorted or not, it will always take n log n time. So this statement is false. Now let's take a look at statement 2, Bubblesort. We'll have a better look at Bubblesort here. So what we do in Bubblesort is, starting from the first element in the array, we'll be looking at each adjacent elements in the array, and if a of I is greater than a of I plus 1, we'll be swapping a of I and a of I plus 1 like this. If this element is greater than this element, we'll be swapping this. This we keep on doing for, after that we'll be doing it for a of 2 and a of 3, after that we'll be doing it a of 3 and a of 4. Likewise, we'll keep on doing it till the end of the array in one iteration. So what happens at the end of that iteration is, the largest element in the array will reach at the rightmost end. After that, we'll start the second iteration from the start of the array to the second last element of the array. After that, and we'll be doing the same swapping procedure. After that, the second largest element will be reaching at the second rightmost position in the array. After that, we'll again do the same procedure in the next iteration, only that this time we'll be doing it from the start to the third last element in the array. This we keep on doing. After that, the array will be sorted. Now that is how Bubblesort works. But after each iteration of this swapping, if we count the number of swaps made during that iteration, and if that count is 0, then we can stop the procedure there itself, because after one iteration, if the number of swaps made is 0, which means it will mean that each element will be less than or equal to the element to the right side. Now if each element in an array is less than or equal to the element to the right side of the array, that means the array is in sorted order. So if you take a look again in an iteration, count the number of swaps made during that iteration, and if that count is 0, we can stop Bubblesort procedure there itself, as the array would already be sorted. Now this particular step, in some textbooks in the normal implementation of Bubblesort, this particular step won't be there, but in some textbooks this particular step will be there. So in some textbooks, if we are including this, they call it modified Bubblesort, but in some textbooks, even without calling it modified Bubblesort, they will include this and they'll call it Bubblesort only. So if this step is included, we'll see that if the array is in sorted order, it won't need any more iteration. It will need only one iteration to find out that the array is in sorted order, and it will stop there. So if we include this particular step, complexity of Bubblesort will become theta n if the array is sorted. If this step is not included, then the complexity of Bubblesort will be theta n square. But in this question, for our consideration, so we don't know which they are considering, though we will keep this in hold. We will look at statement 1. Quicksort runs in theta n square time. So in normal implementations of Quicksort, we take the rightmost or the leftmost element as the pivot element. Sorry, this made a mistake here. In normal implementations of Quicksort, we take the rightmost or the leftmost element in the array as the pivot element. So if we are doing that, then and if the array is in sorted order, then the complexity of quicksort will become theta n square. Now this is known. So if you are taking the rightmost or the leftmost element as the pivot element in quicksort, if the array is sorted, that quicksort runtime will become theta n square time. That is the worst case running time of algorithm. So for this question, we will consider this as correct. In that case, we can consider this Bubblesort as the modified Bubblesort only, which will include this, which will mean that the Bubblesort can run in theta n time, meaning that saying Bubblesort runs in theta n square time is false. So the correct answer is 1 and 4, that is option D.